Um, I want to acknowledge my co-authors, Josh Peterson and Justin Robinson. They're here in the room today. If you have difficult questions at the end of the talk, I would like to direct you to them for some answers. I think most of you by now are familiar with Groundwork Renewables. We're focused entirely on delivering high-quality ground-based measurement data sets for the solar industry. Our programs are built around solving a lot of the problems with ground data that people have alluded to in the talks yesterday and even just now this morning. We've enjoyed having what we see as a pivotal role in the energy transition, and we are working toward our goal to accelerate the success of solar in leading the utility scale energy production. Our equipment and services support the full solar project lifecycle from pre-construction resource assessment through operational performance monitoring. Ultimately, though, our star product is that high quality data. The focus of my talk today is on soiling data. Soiling data, no matter how high quality it is, requires significant post-processing in order to make sense. And based on the conversations we've had with performance engineers and IEs and quite a few of you in this room actually, making sense of that data is tricky. I'm going to do a quick review of how soiling is measured. Then I'll dig into some of the challenges that soiling data presents and give you some pointers on how to deal with those. And finally, I'll talk you through how soiling rates can be determined from those data and how we can estimate the uncertainty associated with those soiling rates. So just a quick review of how soiling is measured. The industry standard method is this paired PV device method. We have with a matched set of 2 PV modules. In resource assessment, we use mini modules like the ones that you see in this picture. The modules are installed side by side at a fixed tilt, and one module is kept clean while the other module is left to soil naturally. Soiling reduces the amount of sunlight that's able to reach the module, and so that reduces the short circuit current output. And when we compare the short circuit current output of the soiled module to the clean, that gives us a measure of the extent of the soiling. So in our programs, the clean module is cleaned weekly, and the soiled module is cleaned occasionally by wind, dew, or rain, occasionally also cleaned manually. We call that a soiling kit reset, and we do that if the soiled module is disproportionately impacted by something like bird droppings or agricultural sprays, stuff like that. So cleaning the soiled module, whether it's done manually or naturally, resets the study and brackets a soiling period, and I'll talk about those later. We also measure rainfall concurrently, and data from the system in our programs are collected at the 1-minute interval. So when we talk about soiling, it's important to clarify the difference between soiling ratio, soiling rate, and soiling loss. Soiling ratio is an instantaneous measure of the reduction in the module output due to that soiling. So what's happening on that module right now. Soiling rate is a measure of how fast that soiling ratio is changing through time. And it's calculated by dividing the change in the soiling ratio over the amount of time that change occurred. Soiling loss, or more specifically production loss due to soiling, is a derate of power production. When it comes to soiling loss, there's a distinction between how we look at soiling measurement data in pre-construction and how it's used in plant operation. In pre-construction, the goal is to be able to predict soiling losses over the long haul once the plant is in operation. And as this group knows, this is done using models. There are various published models out there, and some performance engineers and IEs have come up with their own models to generate these numbers. And model inputs vary. Soiling rate, particulate matter, weather such as rain are all among those inputs. And some models use that soiling rate data, but the calculated measured soiling rates can also be used to check models that don't use soiling rate data. In post-construction, during operational times, you all probably know this more than I do, soiling loss is monitored in real time and is simply just by monitoring the soiling ratio. So if your expected output is 1, you subtract the soiling ratio, and multiply that times 100, and that's the percent of loss that you're going to get due to soiling. However, also, the approach to data processing that I'm about to talk about can be applied to operational data in retrospect. And in fact, a lot of the methodology that we use comes from a paper published by NREL that was using production data to estimate soiling losses. So anyone who's looked at soiling data would agree that it's hard to make sense of, especially here in the United States, where soiling rates tend to be pretty low and fall kind of within the uncertainty of the measurement itself. The IEC 61724-1 performance monitoring standard outlines kind of some basic guidance for how to filter and average soiling data, but it gives a lot of leeway in terms of how you filter the data. A number of papers have been published on this. Pointer here. There we go. Yeah. Papers have been published with different approaches to filtering. The most recent one on my list is actually a paper that we just, is the proceedings paper from this year's PVSC. And a lot of the filtering that I'm going to talk to you about today is in that paper. You can find more details there. So the challenge to filtering and averaging to a daily value, which is what the standard recommends, is that even if you have a quality number, that quality number doesn't really tell you much about the spread in the data over the course of the day. So when the error bars are unknown, it's hard to know if the ups and downs over the course of a day are real or if they're in the noise. So pretty simple demonstration here. Same data in green on the left and on the right. On the left, you can see the error bars are so big that you can't really tell that anything's changing from one day to the next there. And the slope of the soiling rate is really the slope of the line. So as you see the soiling ratio decreasing, you're getting more and more soiling. And so the soiling rate for this particular site could range from anywhere from there to there. So it could be soiling rapidly, or it could be soiling hardly at all. If you can do significant data filtering and get the error down in your measurements, you can have a lot more confidence in what those slopes are. And again, those slopes are indicative of the soiling rate. So let's talk about the things that contribute to those error bars. Incoming irradiance needs to be sufficient to generate a strong enough signal to overcome the noise. And when irradiance levels are low, module outputs are small. And when you're taking a soiling ratio, you have a ratio of two small numbers. You tend to get a lot more variability in those numbers. And speaking of variability, and at the risk of sounding like a broken record, soiling data can be very noisy. Filtering noise really, the approach to that is really just averaging over the course of a day. You get a lot of chatter in those data. That noise can come from variable sky conditions, variable module surface characteristics, birds flying over. You have two sensors with a large surface area. So you're bound to get a lot of noise in there. Outliers fall outside of the inherent noise, so they need to be filtered out completely so that they don't skew averages that occur on a daily basis. And then angular response is a big one. The standard talks about this. Data are less accurate when the angles of incidence onto the module are larger, and a couple of people touched on that yesterday. You get refraction through the glass. And then data are, let's see, sorry about that. Go back one. Another gotcha is that data are skewed across the solar noon window when the modules aren't coplanar. So just to explain that, if you have one module that's tilted further east, your soiling ratio is going to be high in the morning and then low in the afternoon, for example. One thing that the standard doesn't touch on is this clean control idea. The standard assumes that the clean module is clean and the soiled module is soiled. Well, the clean module doesn't stay clean. For example, if you're doing weekly maintenance events, by the time you get to the end of the week following maintenance, that clean module might have accumulated soiling at the same rate as a soiling module. So your soiling ratios are going to be skewed, and I'll go into more detail on that. Okay, so now I'm going to start going into how do we overcome these challenges that I just presented. We'll start with insufficient irradiance. A minimum of 500 watts per meter squared is kind of the standard threshold that you're going to see in the literature. This threshold is more likely to be exceeded in the summer than the winter, and more likely to be exceeded in, let's say, Texas versus Maine. So we can't control how sunny it is, but we can be more sophisticated about how we determine that threshold. And when we process soiling data at Groundwork, we actually set a dynamic threshold that's based on the extraterrestrial irradiance. So our threshold goes up and down based on where you are in the world and what day of the year it is. We also set a hard lower limit of 200 watts per meter squared on this, because once you get below 200 watts per meter squared, the data get to be pretty squirrely. So next we'll talk about how to deal with inherent noise and outliers. And the graph here is showing soiling ratio data over the course of a single day. So this is like the solar noon window on that day. We have a lot of data that just behaves pretty well. There's this, a lot of chatter in it, that's some noise. But then we see that there are points that fall outside of that nice smooth line. And, to our eye, we can see that those are outliers, but we need a way to throw those out. So we just do that statistically by calculating the median, and then the 5% and 95% value. And then we double those distances and throw out anything that falls too far away from that median. Similarly, we want to get rid of noise that falls outside of a single day. So previously I showed you what happens over the course of a single day. This is kind of the day-to-day variation. So over here, each of these sort of vertical clouds of data is the solar noon window on a single day. That's the range of data for that day. So as we step through the days, these days on the left, these are kind of the before days. This is the current day. And then these are the after days. What we're doing here is we're looking backward from each individual day, and we want to see if the day in question is matching the trend going backward. And then we also look forward, and we filter out anything that falls outside of that. And this particular day could have happened if you were only looking forward. It could have happened because, let's say, both modules got dirty over the course of the week. The clean module was cleaned, so the soiling ratio just dropped like a rock. And conversely, going from here to here could actually be real if you had something like a soiling kit reset where the soiled module was clean. That would bring the soiling ratio back up. But if there are data that fall outside of the backward trend and the forward trend, then we know that we can kick those out. And so then the data over on the right, that's about 18 months worth of data. And this data were pretty noisy until we applied those last two filters that I just described. The X's are showing what was thrown out as outliers, and then maybe harder to discern are these red circles that were thrown out as a result of that forward-backward filter. So really chipping away at all the data that we've got here. So moving on to angular response. This happened, module misalignment can be a big deal. And the IEC standards specifies that modules should not be, or they need to be coplanar within a ½ degree of one another. And that ½ degree is, it's pretty stringent tolerance, and you can get that at installation if your installers are paying attention to what they're doing. But you can imagine that once a tracker starts tracking, or once like a resource assessment tripod settles a little bit, or cleaning happens, you might end up getting those a little bit out of alignment. And that can have a big effect on the soiling ratio. So as I mentioned earlier, in this example, the soiled module is tilted a little bit toward the east. And because of that, in the morning, you get a larger short circuit current from the soiled module. And then in the afternoon, you get a smaller short circuit current. And that actually is going to skew your soiling ratio. So over the course of a single day, your soiling ratio might drop this much. So from being slightly above 1 to 0.994. And the data that are shown in this graph are 4 different colors, because that's 4 different days where that pattern just repeated itself. And so if we're trying to reduce the uncertainty in these data, we've got nice trends happening here, but the error bar, if you average all this data together, the error bar is pretty large. So what we've done is we've introduced a flattening adjustment. And that flattening adjustment basically just takes that line and kind of spins it so that it's horizontal. We do this so that all of the noise around that trend line is maintained. So you can see we still have that scatter preserved, but the overall spread from top to bottom in this day of data is reduced, I think, by about 3x in this case. So shrinking those error bars. Okay, and then the last one we'll talk about is the idea of the clean control. And so this is maybe a little bit extreme example, but this shows what happens at a particularly dirty site that has weekly maintenance. We've got a few, let's see, maybe 4 weeks worth of data here. These vertical dashed lines are maintenance events. So if we start, there was a maintenance event right before this data starts, and as you step through the week, both the clean module and the soiled module are getting soiled at the same rate. So the soiling ratio just stays the same. Once you get a cleaning event, that soiling ratio drops, and then it stays the same for a while again. So when we have data like this and we want to calculate soiling rates from maybe one day to the next or 1 month to the next, and we have a large scatter of the data in here, it's kind of hard to pull a rate out of there. So the rate could be anywhere from, being steep like this to being flat like this. So the way we get around this is that we actually just don't even look at data that doesn't happen after a cleaning event. In our programs, we have pretty reliably weekly maintenance. We've got the maintenance button pushes in the data. So we're able to just import that information and use it to filter out data that may not represent a clean module. Let's see. There we go. All right, so the series of graphs here is just kind of a recap, and it illustrates how each of the data filters contributes to a cleaner data set. We start with the data on the top and filtering out data where the irradiance was too low. Oh, I need to mention that we do narrow to a solar noon window of plus or minus 2 hours. So it's a 4-hour window. That's what the IEC standard recommends. I've seen everywhere from a 1-hour window to quite a bit longer window. If you have a tracking system, your angle of incidence stays small throughout the day, so you can extend that window. So these are solar noon window data. We filter out insufficient irradiance. We filter out outliers. We do that flattening adjustment, and then that forward-backward filter kicks out some inter-day outliers, and then at the very bottom, we're kicking out data when we can't be 100% sure that the clean module is clean. And so what we're left with is those tiny bits of data, and they don't look like a whole lot, but they're still sufficient to calculate soiling rates, and I'll show you some examples of that. All right. So once the data are filtered, we are almost ready to calculate soiling rates. But before we do that, we need to break up the time series into soiling periods. And I mentioned earlier, soiling periods are kind of bracketed by those cleaning events. So the cleaning events could confound, trying to calculate soiling rates. So cleaning events, again, can be manual or they could be natural. And I think I already mentioned that manual resets are when the technician actually goes out there and physically cleans that soiled module. And natural resets are mediated by typically weather, rain, wind, or dew. And we found that the stochastic rate and recovery method, which I think is actually built into RD tools, was provided some really good guidance for determining automatically when a cleaning event occurs. So, a cleaning event is really characterized by a jump up in that soiling ratio. So now that we've got everything broken up into soiling periods, we can calculate the soiling rates. So when we distill these data down and we have the remaining data points, we can calculate rates between any point on one day and any point on either a future day or a subsequent day. And the soiling rate is just by definition the slope of the line in a time series graph. So we draw lines between all of the data points that we have in the soiling period, and that gives us a collection of rates to aggregate and do statistics on. So for a 1-year campaign, we typically get about 500,000 slopes, and those individual slopes can be aggregated into, for example, monthly or annualized values. That's typically what people are looking for. And because the 1-minute data we use, the volume of data that we have is sufficient in order to calculate the statistics to describe the uncertainty in that ratio, or sorry, in those soiling rates. And when we talk about uncertainty, this is in the paper, we're talking about kind of the spread in the soiling rates over the course of that time period. So we report the median, and then the uncertainty is the distance between the low 5% value, or the P5, and then the P95 on the high end. Okay, thanks. Wrapping up. So let's take a look at a couple of months of data. The top graph shows the mix of slopes that one would get if no data filtering were to occur. And then the bottom graph shows what happens when we actually apply all of those filtering rules. And to illustrate this further, if you actually take the soiling rates, so the slope of each of those lines, and plot those in a time series, this is what we get for soiling rates. So you can see, I mean, this is an extreme case. I'm sure some filtering is done on all data, but without pretty stringent filtering, you could end up with kind of just a mess, and you can't really tell what's happening there. I'm going to zoom in a little bit on that lower right-hand graph. If you zoom way in, you can see we still get kind of a spread over the course of each of these days in the soiling rates, but that spread has been much reduced. And that spread, like I said, from top to bottom, this kind of gives you a sense of the uncertainty in that value that you've derived. We actually we processed a lot of soiling data sets. We looked at 32 data sets that were spread out across the United States. And we came up with this value for a groundwork measurement system that's maintained weekly, where we process the data. We get the uncertainty down to be pretty low. So that was a bit fast and furious, but hopefully that all made sense to you all. And if it didn't, you can talk to Josh and Justin.